This last video for Chapter 6 is the review for the chapter. So I would assume you would do this on the week that you're going to be taking the test. And that test has to be turned in to me, completed, by April 24th at 4 o'clock. So please remember that. Now, if you look at these two problems, 1 and 2, it says, what's the difference between the two? Well, the difference here is actually that this top one has restrictions. It's in degrees, but it's restricted to 1 rotation. Whereas the bottom one has no restrictions. It says all degree solutions. So that's the one where you'll have multiples of 360 added to each answer. Okay? Let's take a look at some of each type of problem that you'll be tested on. Now, when you look at this one, what has changed in this one is the question. And what has changed here is that we have multiple angles. When you have multiple angles, remember we have x is trapped between 0 and 360. So we would have to multiply this by 3. And we would find that our 3x is trapped between 0 and 1080 degrees. So 3x can go 3 rotations. Okay, let's do some actual problems then. This chapter began with what we call basic trig equations, solving them. And again, these were some that you may have encountered in Algebra 2, depending upon your teacher. We always start out by looking at what units we're in. We're in degrees. And we're restricted to 1 rotation. The process for solving it involves first isolating the trig function. We want to get the cosine x by itself. To get the cosine x by itself here, we would subtract 1 and divide by 2. So cosine x equals -1/2. Then we decide, is this a quadrantal angle or is this a reference angle type situation? This one is a reference angle. The angle in degrees whose cosine is 1/2, positive 1/2, is 60 degrees. We have a negative cosine. Cosine is negative in quadrants 2 and 3. In quadrant 2, we're moving up 60 degrees. So to get this angle, we would take 180 and subtract 60. So our quadrant 2 answer will be x equals 120 degrees. Our quadrant 3 angle, we have to go down 60 degrees. So our quadrant 3 angle will be 180 plus 60 degrees. So x would equal 240 degrees. No need to check these answers. We did not square both sides, so I boxed them immediately. The next problem is once again in degrees and still restricted to 1 rotation. We'll isolate the trig function. So the tangent of x will equal -1 over square root of 3. Now we might be more familiar with that in its rationalized form. And this one we can see is also a reference angle again. The angle whose tangent is square root of 3 over 3 is 30 degrees in degrees. Tangent is negative in quadrants 2 and 4. Quadrant 2 we've talked about. In quadrant 2, we have to go 30 degrees up. So we would have 180 minus 30. So in that one, x would be equal to 150. Quadrant 4 we haven't yet talked about in our review. We're going 30 degrees down from the x-axis. So really it's a full rotation, 360 minus 30. So in quadrant 4 we end up with 330 degrees. Again, no need to check, no need to not box them or anything like that because we did not square both sides. Question 3. When you look at question 3, now as you can see the units have changed. We're now in radians, but we're still one rotation. We're going to isolate the cosine. We have cosines on both sides. We'll want to get the cosine all to one side. I'm going to subtract the 5 cosine x to begin with. So square root of 3 plus 2 cosine x equals 0. Subtract the square root of 3 and divide by 2. I find that cosine of x, negative square root of 3 over 2. This one yet again has a reference angle. The reference angle in radians, well, in degrees it would have been 30 degrees. In radians it'll be pi over 6. Cosine is negative. Cosine is negative in quadrants 2 and 3. And this one's in radians, so we're going to talk about that. So in quadrant 2, I'm going to go pi over 6 up. Well, a full rotation up to here, a full half rotation, I should say, would have been 6 pi over 6. So if I take 6 pi over 6 and I subtract 1 pi over 6, I find out that I get 5 pi over 6. 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. Quadrant 3. Quadrant 3, I'm going to go down a pi over 6. And this part right here would have been a full pi again, which was 6 pi over 6. So I'm taking 6 pi over 6, and I'm adding 1 pi over 6. So in quadrant 3, I get 7 pi over 6. And that one was in radians, still one rotation. Question 4. Question 4 is still radians, still one rotation. We're going to isolate the sign. First, I'll begin by getting all the signs to one side. So 2 sine of x plus square root of 2 equals 0. To isolate the sign, I will subtract square root of 2 and then divide by 2. Sine of x equals negative square root of 2 over 2. This one does have a reference angle. The reference angle in degrees would have been 45. In radians will be pi over 4. Sine is negative. And sine is negative in quadrants 3 and 4. Quadrant 3 we have talked about. I'm going a pi over 4 down. A full pi would have been 4 pi over 4 up to here. So I have to go 4 pi over 4 plus an additional pi over 4. So in this quadrant, quadrant 3, I get x equals 5 pi over 4. Quadrant 4, again, I'm going down pi over 4. So to get this angle, I'm actually 2 full pi's minus 2 full pi's would be 8 pi over 4. So I'm going to take 8 pi over 4 and subtract a 1 pi over 4. So in quadrant 4, I get 7 pi over 4. We were in radians, still one rotation. Now this one, if you look at the directions, it says to the nearest tenth. It's in degrees. So this is one where we're likely going to need a calculator. We'll still isolate our trig function. Cosine x equals negative 2/3. Now cosine negative tells us that we're in quadrants 2 and 3. But to get our reference angle this time, we have to take the inverse cosine of 2/3. Notice we don't use the negative again for reference angles. When I do that on my calculator, inverse cosine of 2/3, to the nearest tenth of a degree, I get 48.2 degrees. In quadrant 2, I would have to take 180 minus 48.2. I get 131.8. In quadrant 3, I would have to take 180 plus 48.2. And in quadrant 3, I get 228.2. Again, no need to check, so I box them immediately. This one says round to the nearest tenth again. We're still in degrees. I'm going to move all of the cosines to one side by adding a 6 cosine x. Gives me 7 cosine x minus 5 equals 0. Isolating the cosine, I get cosine x equals 5 over 7. Cosine is positive. Cosine is positive in quadrant 1, quadrant 4. To get my reference angle, I have to take the inverse cosine of 5 over 7. Rounding to the nearest tenth. I get 44.4. Quadrant 1 is the reference angle, so x equals 44.4 degrees. Quadrant 4, I would have to take 360 and subtract 44.4. And I get 315.6. Not much different than the previous problem. Still degrees, still rounding to the nearest tenth, and only one rotation. Now this one we're in radians, and we're one rotation, and it doesn't say to round. This one actually factors. We can factor out a GCF of cosine x. If I factor that out, I'll have a cosine x that I factored out. Then I'll have a 2 cosine x plus 1 equals 0. Set each of those factors equal to 0. The first one is already solved. It's already isolated for cosine. The second one, I subtract 1 and divide by 2. So let's talk about this first one. Now the first one, cosine x equals 0, that's quadrantal. Remember, cosine is equal to the x over the r. So we're looking for the places on this unit circle where the x is 0. So that looks to me like it's going to be up here and down here. Both of those will have a cosine equal to 0. So for this one, I get x equals, and I guess we would have 90 degrees, which is pi over 2, and 270 degrees, which is 3 pi over 2. For the second part, this one has a reference angle. The angle whose cosine is equal to 1/2, well, it would be 60 degrees, but in radians that would be pi over 3. We have a negative cosine. Negative cosine tells us we're in quadrant 2 and quadrant 3. In quadrant 2, I would have to take a full pi, which would have been 3 pi over 3, and subtract 1 pi over 3. So in quadrant 2, I get 2 pi over 3. In quadrant 3, I would have to take a full pi, which is 3 pi over 3, and add pi over 3. So in quadrant 3, I get 4 pi over 3. Notice I boxed them immediately. No need to check. We didn't square both sides. We just factored. In this one, we're in radians again. And we're going to factor. So this one's a general trinomial. I'll factor it into 2 sine x and sine x in the front, 1 and 1 in the back. I need a negative there and a positive there. Set each of those two factors equal to 0. Here I'll subtract 1 and divide by 2. And in the right one, I'll just add 1. The left one has a reference angle. Well, the sine would be equal to 1/2 for 30 degrees, which is pi over 6 in radians. We have a negative sign, which tells me we're in quadrant 3 and quadrant 4. In quadrant 3, we would take a full pi, which is 6 pi over 6, and we'd add another pi over 6, so I end up with 7 pi over 6. In quadrant 4, we would take 2 full pi's, which is 12 pi over 6, and we would subtract 1 pi over 6. So in quadrant 4, I get 11 pi over 6. Take a look at that one, pause it if you need to. The next question. Well, as you can see, we have now switched to degrees. But this one still factors. There's a common factor here of cosine x. So we would separate them. Oh, let me get back to that problem. Sorry about that. So we'll factor out a cosine x. Oh. And we'll have sine x plus 1, dividing everything by cosine. Then we said each of those factors equal to 0. The first one's already isolated. The second one will subtract 1. And both of these are quadrantal. We've already seen that the cosine of x is equal to 0 for, well, the top and the bottom on our unit circle. The top corresponded to 90 degrees. The bottom corresponded to 270 degrees. Because both of those points have a 0 for their x. The sine, on the other hand, is the y over the r. So this time we're looking for the point where the y is -1. Well, that would correspond to 270 degrees. Since I already have that one boxed, I don't need to box it. If I wanted to, I could box it again. It's just not required because it's already been reported as a solution. Okay, next question. Now, this one tells us to round to the nearest tenth, and it doesn't factor. Since it doesn't factor, we're going to have to use the quadratic formula. So the sine of x would be equal to, now I need negative of b, and then plus or minus the square root of the b squared minus the 4 times the a times the c. All of it divided by 2 times the a. So really, we have the sine of x equal to, negative of -4 is just 4, plus or minus, and then beneath the radical, we have 16 minus 8, which is 8. As we've seen on previous problems when we use the quadratic formula, that actually gives us 2 possibilities. Sine of x is equal to the 4 plus the square root of 8 over 4, and sine of x is equal to the 4 minus the square root of 8 over 4. Let's talk about this top one up here. If I take 4 plus the square root of 8, and then I take that total, and I divide it by 4, I get 1.707. Now, sine of x can't be bigger than 1. So this one will give me no solutions. I won't box that yet because there could be solutions to the other part of the problem. So let's take a look at the other part of the problem. So for the other part of the problem, if I take 4 minus the square root of 8, 4 minus the square root of 8, and then I take that total and I divide it by 4, I get this decimal, 0.292829, and it keeps going. Well, this one can give us some values, but it certainly isn't going to be quadrantal, and it isn't going to be one of our reference angles 30, 45, or 60. So to get our reference angle, we'll have to take the inverse sine of that number that we got when we worked this out. And my reference angle to the nearest tenth comes out to be 17.0 degrees. And it was a positive sign. So that means we were in quadrant 1 and quadrant 2. Quadrant 1 is the same as the reference angle. So x would be equal to 17.0. Quadrant 2, I have to take 180 and subtract my reference angle. So I get 163.0. And once again, I box them immediately because there's no need to check it. We didn't square both sides, so there's no possibility of an extraneous solution. Okay, a couple things have changed here. We have multiple angles, and we have no restrictions. So that means we're actually looking for all possible answers to that. Now, the tangent is actually already isolated. So we begin by thinking of, is there a reference angle or is this quadrantal? And there is a reference angle. The angle whose tangent is square root of 3 is 60 degrees in degrees. And we do have a positive tangent. Tangent is positive in quadrant 1 and in quadrant 3. Now, in quadrant 1, that's our reference angle. So the 2x that's inside of the trig function will be equal to 60 degrees, but that's only on the first rotation, and we can go any number of rotations. So to indicate the any number of rotations, each rotation is 360, so I add 360 times n. N's the number of rotations. We'll come back and finish that one in just a moment. In quadrant 3, our 2x would be equal to, now quadrant 3, I have to take 180 and add 60, so that gives me 240, and then I add the 360n. And now we're going to go back and finish those. Of course, we actually want to solve for x, so we have to divide everything by 2. If we divide everything by 2, the quadrant 1 answers are 30 degrees plus 180n. For the quadrant 3 answers, we divide by 2, we get 120 degrees plus 180n. So that was a multiple angle problem. Okay, let's take a look at number 12. Number 12, same type of problem. Once again, multiple angles. And we're in degrees. This one also has a reference angle. The sine is already isolated. So the reference angle would be a sine of 60 degrees. So 60 degrees. We have a negative sign. Negative sign indicates quadrant 3 and quadrant 4. In quadrant 3, the inside, the 3x, would be equal to, and here we have to take 180 and add 60, so 240. Since there are no restrictions, we would add 360n. In quadrant 4, our 3x would be equal to, this time it's 360 minus 60, so that's 300, and again, plus 360n. And to finish it, we have to divide everything by 3. So x would be equal to 80 degrees plus 120n. That's quadrant 3. X would be equal to 100 degrees plus 120n. That would be our quadrant 4 answers. Next one. Okay, once again, degrees, no restrictions. And this one, I believe, does factor. I think we can use 2 sine x in the front of each of them, a 1 in the back, and both have to be a minus. Negative 2 sine x and negative 2 sine x does in fact give us negative 4 sine x. Since both factors are the same, we really only have to set one of them equal to 0 and solve that. To set both equal to 0 would be redundant. This one does have a reference angle. In degrees, it would be 30 degrees. Positive sine. Sine is positive in quadrants 1 and 2. In quadrant 1, we would have x would be equal to our reference angle. Since there are no restrictions, we'd have to add 360n, and that is finished. In quadrant 2, we would take 180 minus 30, which would be 150, and we'd have to add 360n. Okay. The next problem. Now, this next problem says all solutions, and we're still in degrees. We have 2 different trig functions. But if we think about this for a moment, we can rewrite using identities. And I think that will help. The cosecant can be rewritten as 1 over the sine of x. The cotangent can be rewritten as cosine x over sine of x. And right now, we know sine of x cannot be 0 in this problem because it would be undefined. Since we know it cannot be 0, we can then multiply everything on both sides by sine of x. And that will make it a much simpler problem. When I multiply in this first one, I just get 1. The signs cancel. When I multiply in the second one, the signs cancel again. I have 2 cosine x. And on the right, 0 times sine is 0. It's now a much simpler problem. To isolate the cosine x, I'll subtract 1, divide by 2. This one has a reference angle, 60 degrees. We have a negative cosine. Cosine is negative in quadrants 2 and 3. In quadrant 2, our x would be equal to 180 minus 60, which would be 120. But because we have no restrictions, we add a 360n. And that's one of our answers. In quadrant 3, our x would be equal to 180 plus 60, which is 240. Oh, sorry about that. And once again, no restrictions, so plus 360n. Okay, next question. Number 15. Now, number 15 has switched to radians, and we have 1 rotation. We have 2 different trig functions, but it's not possible to use identities. We don't have one that works. So we're going to separate and square both sides. That'll require us to check at the end. So to separate, I'm going to move this one over, just so that I end up with all of the ones with square root of 3's on the same side. So I'm going to subtract square root of 3 sine x. That will leave me with a cosine of x equals square root of 3 minus square root of 3 sine x. And now we're going to square both sides. That's going to require us to check at the end. So that would leave me with cosine squared x equals, when I square the square root of 3, I get 3. And then 2 times square root of 3 times negative square root of 3 sine would be negative 6 sine x. And when I square the last one, I get plus 3 sine squared x. Now we'll use the Pythagorean identity. And the Pythagorean identity says this can be rewritten as 1 minus sine squared x. Finally, everything's in terms of just sine x. So we'll move everything over so we have 0 on one side. Adding a sine squared x, I get 4 sine squared x minus 6 sine x. And then subtracting 1, I get plus 2. I'm going to divide everything by 2. So I would have 0 equals 2 sine squared x minus 3 sine x plus 1. And this one I believe will factor. So we're going to factor. We'll have 2 sine x, 1 and 1, both are negative. Set each of those equal to 0. Isolate the sign. Isolate the sign. This one has a reference angle. In degrees, it would have been 30. In radians, it would be pi over 6. Positive sign means we're looking at quadrant 1, quadrant 2. Quadrant 1, we would have x equals pi over 6. Quadrant 2, we'd have x equals 5 pi over 6. This one is quadrantal. It would give us x equals pi over 2. And now, so that we don't forget, you have to check. So when I put in pi over 6, the sine of pi over 6 would be 1/2. The cosine of pi over 6 is square root of 3 over 2. So I'd have square root of 3 over 2 plus square root of 3 over 2, which is 2 square roots of 3 over 2, which is square root of 3. So this one checks. When I put in 5 pi over 6, well, unfortunately, 5 pi over 6, the cosine is negative. So this one does not check. This one's extraneous. Now, pi over 2, the sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this one does check for the quadrantal one. You always have to check when you square both sides. Okay, we're getting close to the end. I know this is kind of long. So we're in radians. And it's a secant. I can change that to a cosine by taking the reciprocal. And that's what we should do. So we have a reference angle. Cosine equal to 1/2. That would be 60 degrees in degrees. So pi over 3 in radians. Positive cosine indicates that we're in quadrants 1, quadrant 4. Quadrant 1 is our reference angle, so pi over 3. Quadrant 4 would be a full 2 pi's, which would be 6 pi over 3 minus 1 pi over 3, so we get 5 pi over 3. No need to check, didn't square both sides, only going one rotation. Okay. So radians, no restrictions. Multiple angle. Okay, we're going to isolate. Cosine of 3x equals square root of 2 over 2. Reference, be 45 degrees, so that's pi over 4. Positive cosine, so that tells me quadrants 1 and 4. Quadrant 1 is the reference angle, so my 3x will be equal to pi over 4, but I can go any number of rotations, so I have to add 2 pi n. Quadrant 4, my 3x, the inside of the trig function, will be equal to, well, it's 2 full pi's, which is 8 pi over 4 minus 1 pi over 4, so I get 7 pi over 4, and then plus 2 pi times n. And finally, to finish up, we have to divide by 3. Easiest way to divide a fraction by 3 is to multiply the denominator by 3. So I get pi over 12 plus 2 pi over 3n. Here, 7 pi over 12 plus 2 pi over 3n. Number 18. Okay, you can see we're in radians and only one rotation, and it's multiple angles. So first of all, if I multiply by 3, I see that my 3x can go to 6 pi, so 3 rotations. Okay, we do have a reference angle. The reference angle here would be, well, in degrees it would have been 30 degrees. In radians it would be pi over 6. Negative cosine tells me that we're in quadrants 2 and 3. First rotation. First rotation, the 3x would be equal to, in quadrant 2, it's a full pi, 6 pi over 6, minus 1 pi over 6, so it's 5 pi over 6. Quadrant 3, the 3x would be equal to, well, this time it's 6 pi over 6 plus pi over 6, so it's 7 pi over 6. Now, those aren't finished yet. We'll come back and finish them in a moment, but let's talk about the second rotation. On the second rotation, we're adding 2 full pi's. So 5 pi over 6 plus 12 pi over 6. So the 3x would be equal to 17 pi over 6. Over here, quadrant 3, adding a 12 pi over 6, we get 19 pi over 6. And don't forget, we have a third rotation. On that third rotation, we're yet again adding another 12 pi over 6, 2 full pi's. So the 3x would be equal to 29 pi over 6. And here the 3x would be equal to 31 pi over 6. And we still have to finish that. So when we finish it, we divide by 3. On this one, we would get 5 pi over 18. Once again, the easiest way to divide a fraction by 3 is to multiply the denominator by 3. On this one, x would equal 7 pi over 18. Here, we'd have x equals 17 pi over 18. Here, x equals 19 pi over 18. Here, x equals 29 pi over 18. Here, x equals 31 pi over 18. Okay, pretty long problem, 6 answers to it. So look this one over carefully. The reason we had 6 specific answers is because of this restriction that was given to us. We couldn't have infinite answers. Okay, we're getting down to the end here. So we're looking for all degree solutions, no restrictions. This one has a reference angle. The reference angle in degrees is 30 degrees. Negative sign. So we're in quadrants 3 and 4. In quadrant 3, the inside, the 4x minus 20, will be equal to, well, it would be 180 plus 30, which is 210. Since we have no restrictions, we would add 360n. Quadrant 4, the 4x minus 20, would be equal to, now 360 minus 30 would be 330, and then again plus the 360n for infinite rotations. We have to finish solving for x, so we'll add 20. We would add the 20 to the 210, we get 230. Then we divide by 4. 230 divided by 4, 57.5. 360 divided by 4, 90. That's my quadrant 3 answers. Adding 20 over here, 4x equals 350 plus 360n. Dividing everything by 4, 350 divided by 4, 87.5 plus 90n. Okay, number 20. When you look at number 20, the first thing you should notice is we have a common factor, so we will factor out 2 sine x, and we'll have 1 plus cosine x. Setting each factor equal to 0. This one we divide by 2. This one we subtract 1. Both of these are quadrantal. The two places where the sign is equal to 0 would occur at x equals 0 and x equals 180. It's the places where the y would be equal to 0. Cosine x equals -1 is when the x is -1, and that would be 180 degrees. We already have that one, so no need to box it. Okay, the last topic in this chapter was parametric equations, and in parametric equations we first try to isolate the trig function. So the cosine of t would be equal to x over 2, and the sine of t would be equal to y over 3. And then we use the Pythagorean identity, sine squared t plus cosine squared t equals 1. And now we're going to replace the sine of t with what it's equal to. So the sine of t is equal to y over 3. So we have y over 3 squared plus the cosine is x over 2 squared equals 1. And we haven't eliminated the parameter yet because we haven't written it in the proper form. So I'll square this, y squared over 9 plus x squared over 4 equals 1. And this would be considered the answer. We also have to classify it or identify it. This one is an ellipse. The center for this ellipse is 0, 0. We move out the square root of 9 in the y direction, so we move up 3 and down 3. The square root of 4 in the x direction, so right 2 and left 2. And then we go ahead and draw our circle. I'm sorry, we draw our ellipse. Okay. The next one. We again isolate our trig functions. So the sine of t would be equal to x minus 2 divided by 3. The cosine of t would be equal to y minus 1 over 3. Since it's sine and cosine, we use the same trig identity, the same Pythagorean identity. We replace the sine with x minus 2 over 3. We replace the cosine with y minus 1 over 3. And we still have to simplify this and put it in standard form. So we'd have x minus 2 squared over 9 plus y minus 1 squared over 9 equals 1. Since both denominators are the same, we'll multiply by 9 on both sides. And that gives us x minus 2 squared plus y minus 1 squared equals 9. That would be considered our answer. This one is a circle. The center is at 2, 1. The radius is 3. So right 3, up 3, left 3, down 3. We go ahead and draw our circle. Okay, the last one on the review. I know this has been a long review. So the last one on the review has secants and tangents in it. We do it the same way. Isolate the trig function. So the secant of t would equal x plus 1 over 2. And the tangent of, sorry about that again. The tangent of t would be equal to y minus 2 over 3. But now we have to use a different Pythagorean identity. We have to use the one that contains the secant and the tangent. So that one is secant squared t minus tangent squared t equals 1. And we'll replace the secant t with x plus 1 over 2. We'll replace the tangent with y minus 2 over 3. And then we will square them. X plus 1 squared over 4 minus y minus 2 squared over 9 equals 1. This one, where we have the subtraction, is the hyperbola. Now the center for this hyperbola is at negative 1, 2. So negative 1 and up 2. We move out the square root of 4 in the x direction, so I move right 2 and left 2. We move up and down in the y direction, the square root of 9, which is 3. 1, 2, 3. 1, 2, 3. And then we sketch that reference rectangle that I talked about when I taught this section to you. And then we draw in our diagonals. So we want to draw the diagonal, which goes extended diagonal. It has to go through the corners of the box and through the center. There's one of them. These are the asymptotes for our hyperbola. And then because we can see that the x came first, it's going to be horizontal. X direction. So it will start on the box here and get close to the asymptote. It will start on the box here, get close to the asymptote. Okay, so there we have it.